Hi, good afternoon, everybody. Today, these sessions, I will be teaching you how to analyze a first order circuit. Okay, but it has steps for you to do, and it's called the shortcut step or step-by-step approach. I found it easier than deriving it, as we have seen in the last sessions. So let's start. Okay, so in the exams, I would be happy that if you can use this method to analyze your problem and get the correct answer, of course. Okay, so therefore we are still at the first order circuit. Okay, so the steps are, as you can see here, I put it down as step 1, 2, 3, 4, 5. Okay, so if you have a first order circuit, okay, you get the first order equations to solve. Well, anyway, in this case we will assume that the solution would be in the form of x of t equal to k1 plus k2 e to the minus t over tau, right? So in other words, your solution will consist of the forcing function, the force response, not the forcing function, I'm sorry, the force response and the natural response, right? This is a natural response and this one is the force response, okay, as we defined, as I told you in the last sessions. Okay, this is step 1. We assume that the solution is in this form. The solution means that if the question asks you for V of t, or the question asks you for the current somewhere in the circuit. Okay, so in this case we represent it as x. Okay, step 2. Okay, well, there in the circuit that you will get, there will be a switch, right? T equal to 0, t equal to second or 3 seconds, whatever. Okay, so then that means that, let's say that if there's a switch, if switch change at t equal to 0, okay, so this is 0, right, time t. Okay, so therefore we will assume that before the switch is changed, okay, the circuit has been in that position. The switch has been in that position for a long time. Okay, for a long time. Then you have to find your VC at 0 minus. So at 0 minus right here, 0 minus, or just before the switch changes. Okay, to do that, since it says that we assume that the steady state has reached before the switch is changed, that means your capacitor is fully charged. So therefore, your capacitor will act like an open circuit, right? An open circuit. If your circuit has capacitor, it will act like an open circuit. If your given circuit has an inductor, right? The inductor at steady state will behave like a short circuit. Okay, so in case of the capacitor, you find VC 0 minus as your capacitor is open. In case of inductor, okay, at steady state, it behaves like short circuit. Then you find IL at 0 minus. That's step 2. Step 3, right? Step 3, the switch change at t equal to 0. Switch change t equal to 0. You want to find out, okay, what happened at t equal to 0 plus, just after the switch has moved. Okay, well, due to another rule of the capacitor is, for the capacitor voltage cannot change instantaneously. So therefore your VC 0 plus will be equal to VC 0 minus. Okay, in some book it will represent it as a voltage source. Okay, for inductor, right, the current does not change instantaneously to a change in the conditions of the circuit. So therefore IL at 0 plus is equal to IL at 0 minus. Okay, so some book would sort of draw it as a current source. Okay, when you do that, okay, you find out at t. So right now you're at t equal to 0 plus, right? Step 2, it's like you are analyze your circuit at t equal to 0 minus. At step 3, you analyze the circuit at t equal to 0 plus. Okay, so you find VC 0 plus, IL 0 plus, depending on which elements is in your circuit. Okay, then with that in mind, with this condition in mind, okay, you find the values that you need to find for the circuit at t equal to 0 plus. So you find the initial values for your answer, okay, at this time, instant in time, t equal to 0 plus. Okay. Step 4 is like you analyze your circuit at t equal to infinities. Right? Switch changes t equal to 0, then you let it run, you let it stay there for a long time again to reach steady state. Okay, you look at what happened to your circuit, draw it out, then find out what is the final values of the parameter that you want to find in the circuit. So x at t equal to infinities. Okay, so these 3 step values you get. Step 5 means you find tau, you find the time constant. You find tau, the time constant. Okay, if it's constant, if it's a circuit with capacitor, resistor and capacitor, RC circuit, your time constant is tau equal to R Thevenin or R equivalent times C, the capacitance values. Okay, if it's inductor, you have inductor in the circuit, your tau is L over RTH or R equivalent, whatever you want to call it. Okay, so that's the case. Okay, to find tau. Then step 6, okay, you substitute your x as in at t equal to infinities as k1. So k1 equal to x at infinities. k2 is equal to x at 0 plus minus x at infinities. So you take the value from step 3 minus the value in step 4. Okay, so this is your constant k1 and k2 in the solution that you have assumed. Okay, so therefore your answer would be x of t equal to x at infinities plus x at 0 plus minus x at infinities, the whole thing's here, times e to the minus t over tau. Okay, or in other words, it means that your answer, your solution consists of x as is a final values, f for final values of that parameters that you want to find, I is the initial values, xi, minus x the final values, okay, then e to the minus t over tau. Okay, so that's the steps. There's only 6 steps. You remember this so-called formulas, the form of the solutions. You have to find in the equation 1 values, 2 values, second values, and tau, the third value. So there's 3 values that you have to find from the circuit. Okay, so life would make it much easier, okay, for you. If this is the case that the switch change at t equal to 0, if you switch somehow change to at t equal to t0, so instead of 0 it change at t0, the switch changes at t equal to t0. The way you write down the solution is that, well, x of t would be still x at infinity, so somewhere here far at steady state, plus x at t0, so x at this point, okay, the value at this point, before it was 0, right, minus x at infinities, and then, sorry, it had to be like this, not like this, okay, e to the minus, okay, because there's a shifting, time shifting, right, so parentheses t minus t naught over tau. Okay, and this is the expression solution for t greater than t0 when, you know, after the switch changes onwards. So this is the step-by-step approach. Okay, so let's look at an example. So therefore, let's look here. Okay, right, simple circuit. Okay, a switch changes at t equal to 0, opens up at t equal to 0 here. Find the current I that passes through 1/3 Henry, an inductor, right? The value of the voltage is 10 volt. Okay, so the steps are, well, this is a R and L, right? RL circuit. So you produce a first order equations for current I. So therefore, let's go. So that's step 1. Let's say step 1, we can sort of ignore it. So step 2, right? You have to find I at 0 minus. So step 2 is when t less than 0 until t equal to 0 minus. So therefore, for inductor at steady state at t equals 0 minus, the inductor would act like a short circuit. So you draw a line instead of an inductor, short circuit, and you have to find I at 0 minus like this. Okay, so you look at the circuit. Oh, also at t less than 0, the switch is still closed, right? So therefore, it closed like this. Okay, so you find the current I. Okay, how does the current flow? Where does the I come from? Well, come from the source, leaving the positive side. Let's go out like this, right? Go through the 2 ohms. Come to these junctions. Oh, should I go 3 ohms or the line that has no resistance? Of course, I would take the easiest path. Okay, so it goes up here. So bypass the 3 ohms and comes down here. So therefore, I is nothing but the current passing through the 2 ohms only. So I 0 minus equal to 10/2, so 5 amps. Okay, right, so next step, t equal to 0 plus, so pretty much at t equals 0 plus onwards. Okay, right, so you have this circuit, the switch opens up, so the 3 ohms come into the picture now. Okay, well, since we know that the current in the inductor through the inductor cannot change instantaneously, so therefore I 0 plus equal to I 0 minus, so equal to 5 amps, right? 5 amps. Okay, right, so next one, step 2, 3, 4. Step 4, find I at infinities. Well, find I at infinities. Well, if the circuit is like this for a long time, right? And it's a DC values, so therefore, right, inductor will act like a short circuit again one more time, right? So this is I at infinities, so 2 ohm, 3 ohms, 10 volt. So therefore, I is equal to, I at infinity is equal to 10 divided by 3 plus 2 ohm equal to 5 ohms, so equal to 2 amps. So you get the initial values for the current that the question asks, and also the final values already. Next one, right, to find tau. Well, tau, right, tau for RL circuit is L over R equivalent. Okay, so that we have only one L, correct, which is 1/3 Henry, right? So this is 1/3 divided by, well, we have 2 resistors. So therefore, we have to find R Thevenin or R equivalent, which is the R total looking from the inductor point of view. So you take out the inductor, look into here, what is R total? So R total is equal to 2 and 3 in series, so equal to 5 ohm. So therefore, your RTH is equal to 5 ohms. So therefore, it's 1/3 divided by 5. So therefore, equal to 1/15 second. So 1/15 second is your tau. Okay, it's your tau. So therefore, with your hopefully the equation, the solution in your head, right? So we can write down right away that, well, I of t is equal to I final, right? Plus I initial minus I final e to the minus t over tau. Well, I final is I at infinity, which is 2. Okay, I at 0, I initial values at t equal to 0 is 5, right? And of course I infinity is 2 again. And tau we found out to be 1 over 15, so this is tau, e to the minus t over tau. So therefore at the end you get your answer as the current would be equal to 2 plus 3 e to the minus 15 t amps. So this is how you perform step-by-step approach. Okay, then let's see this one. Okay, this problem. Okay, find I of t. Find I of t. Right. So let's do it. We have switch changes at t equal to 0. Switch was open, and at t equal to 0 it closed back, right? It closed back. So we assume that it's RC, right? This problem is RC because you have R and 1C. Okay, so it's RC circuit. Okay, so we assume that, well, the answer that we want I of t would be in this form. K1 plus K2 e to the minus t over tau. So step 2 is we have to find the initial values. We have to find VC. We have to find out, well, since we have capacitor, right? Capacitor store energy. We have to find out that before the switch changes, does the capacitor store any energy in it or not? Okay, to check that, we find the voltage across the capacitor. Okay, so find the initial value for VC, right? So at t less than 0, the switch is still open. So therefore, you will write down this circuit. So this is the moment at t equal to 0 minus, right? 36 go to 2 ohms, right? Capacitor has been at steady state, right? So therefore it would act like an open circuit. So you open it up, you have 6K. This branch is nothing to do with it because it's open, right? 4K and then plus 12. So you have to find VC 0 minus. So VC 0 minus, what is it then? Of course, I told you, well, you have to, the key to the to do circuit analysis is current. At least you have to know that the current, how does it flow, how does it go? Okay, well, as a current flow through elements, where are the voltages, what are the polarities for the voltages, drops. So in this case, right, let's say I choose 36 volt giving out the current I total out, right? Now, how does it flow? It flows through here, right? So as it flows through 2K in this direction, so it results in a voltage drop plus minus, let's call it V2, right? Pass through 6K, so plus minus V6, right? Pass through 4K, right? So enter the positive, leave on a negative, V4, right? And then it goes back. So, it's only one loop altogether, right? So it's one loop. Well, there are two sources. I'm not so sure whether it's going to be 36 plus 12 or 36 minus 12, but I will just simply do KVL because it's a loop, right? It's a loop, one mesh. I can write KVL and see what happened, or use mesh analysis to see what happened. So I want to find I total. Why do I want to find I total? Okay, the reason is that if I want to write down what VC 0 minus is, if I want to write down what VC 0 minus, I want to find this, correct? Well, VC 0 minus equal to, and then I walk from the positive to the negative, right? So equal to minus V2, right? Because I walk here this way, I see minus V2, and I'm going to walk from positive this side back to negative of VC 0 minus. So go here, C minus V2 plus 36, and then I reach the negative side. So therefore, my VC 0 minus is equal to minus V2 plus 36. I need V2. And how do you find V2? Well, V2 I can do it by V2 equal to 2K ohms times I total, right? Ohm's law, V equal to IR, RI in this case, what I wrote. So you have to find I total. So to find I total, then I use so-called mesh analysis. Okay, but this is simply, okay, I'm going to write down KVL. So let's write KVL, so you can see for this mesh, right? So it would be V2 plus V6 plus V4 plus 12 minus 36 equal to 0, right? But I want to find current I total. So I total for V2, I have to convert in term of current. So it's 2K I total plus 6K I total plus 4K I total, right, equal to 36 minus 12. So therefore, I total is equal to 36 minus 12 over 2K plus 6K plus 4K, and the answer is 2 milliamps. 2 milliamps. Okay, right? So therefore, I got 2 milliamps I total. I put it back here as 2 milliamps. I can get V2. So therefore, my VC 0 minus is 36 minus V2. V2 is 2K times 2 milliamps. So the answer is 32 volt. So my initial values for the capacitor, voltage in the capacitor is 32 volt. So it has kept some energy in the capacitor before the switch move. Okay. Then next step, of course, this is at t equal to 0 plus. You draw your picture, you draw your circuit in that situations. The switch close, so you have to close the switch here at t equal to 0 plus. Okay. Well, the voltage across the capacitor cannot change instantaneously. So therefore, VC 0 plus is equal to VC at 0 minus. So VC 0 plus is equal to 32 volt. Right? In some book, well, in many cases you see that, well, the circuits actually looks like this. $6K, $4K, and $2K, 36, right? It's VC right here. The circuit's actually like this. We ignore the 4K and the 12 volt altogether, right? Because it's being shorted by that switch. So the actual circuit is like this, right? But you have to keep in mind that this is 32 volt. In some book, right? Well, just to make sure that you don't forget that, they actually write down it as a voltage source at this particular moment in time. At this particular moment in time at t equal to 0 plus, there's a 32 volt right here. So they write it as a voltage source. Okay, and the question is then find I, right? Because the answer you want to find is your I at 0 plus, right? This is step 3, I at 0 plus. So you see at what do you see, right? So you want to find this here. Oh, sorry, 4K is not here. Sorry, I drew it wrong. It should be simply, it's shorted right by 6K right here. Okay, so this is not in the picture. Okay, so if that's not in the picture, so you see that what is I0 plus? Well, I0 plus is a current passing through 6K ohm. Ohm's law, right? So V across 6K over 6K is your current I0 plus. Well, what is a V drop across 6K, right? This node, right? And this node right here, which is linked down here, goes up here, same here. Same, all this is same node. So therefore, the voltage drop across the 6K ohm is 32 over 6K. So therefore, it's 16 over 3 milliamps. Okay, as I0 plus. This is the initial values for your answer for the parameter that was asked in the questions. Then next step, I at infinities. I at infinities. So your original circuit is this 36, a capacitor, 6K ohm, and this is the switch close, right? So this is your I at infinity. So this is the picture, right? The I that you want to find. Well, at infinities, again, right? Current flows like this, come like this, go like this for a long time until we assume, steady state has reached, your capacitor is fully filled, so therefore your capacitor would act like an open circuit. So it would become open circuit. So this is your VC at infinities right here. Of course, we don't look at this anymore because this is short. Okay, so now you have to find I at infinities. Right, this current I. So where does this I come from? Where does I come from? Okay, well, we have one source. So therefore, current goes like this. As I said, always find out how does the current flow. Let's call it I total here. Go pass through K, comes here because capacitor acts like an open circuit. Pass through 6K, goes down the shorted path and back where it started. So you can see again, one mesh, right? And 6K and 2K are connected in series because I total pass through both of them. You want to find the current I, and it happens to be that I total is nothing but your I at infinities. So therefore, I at infinities is equal to 36 over 2K plus 6K. So therefore, it's 36 over 8 milliamps. This is your final values, okay, for the parameter I that is asked in the problem. Next step, find tau. Right, so tau in this case is I equivalent times C, okay, or R Thevenin, right? So this is your circuit, right? So R Thevenin, of course. So R Thevenin, okay. Looking through where the capacitor is, right? Well, of course, this is short, right? You short your voltage source also, okay. So therefore, you see that it's simply 2K and 6K in parallel. Okay, 2K and 6K in parallel. And you get your tau to be 0.15 second. Okay, so R times C. So therefore, you get that your I final is this, right? Your I initial values minus I at infinities is such, okay? And so therefore, your final answer is this. Okay, so this is K1, right? And this is K2. And this is your tau. So that's it for step-by-step problems. So this is, I'm going to wrap up the step-by-step approach. Okay, so more problems will be given to you later in class or online classes that we see each other, online. Okay, so this is a theory. Okay, so that's it for today. Okay, for this topic. Thank you.